Hello class, this is Miss Aya with today's video on sections 12.5 part C, matrices, solving systems of equations. And today we're going to look at how we can use what we know of matrices to solve a linear system of equations. So there's two methods we're going to look at, but first let's take a look at a matrix problem. So let F be an invertible n by n matrix, i.e. square matrix. And invertible means that F has an inverse. So that means that the determinant of F is not 0. And then let X be an n by 1 matrix and let G be an n by 1 matrix, where the following relationship holds. If I were to multiply the F matrix times the X matrix, I would get the G matrix. And as you can see, the dimensions hold, and F is being n by n and X being n by 1 means when I multiply these together, I will get an n by 1 matrix. So the question is, how are we going to use that? Well, suppose we know what F is, and suppose we know what G is, but we don't know what X is. In other words, what are the values that make up the X matrix, which ends up being just a one-column matrix. Well, in order to do that, we can use what we know about inverses. So since F is invertible, then that means that there is a matrix, another n by n matrix called F inverse, such that when I multiply F inverse by F, I'm going to get the identity matrix. Well, if I multiply F inverse by the left-hand side of the equation and the right-hand side equation, then F times F inverse will end up giving me the identity matrix, and the identity matrix times X will just give me X. And then that way I have a way to determine what the solution or the values of the X matrix are by basically multiplying F inverse by G. So let's take a look at an example and see how that goes. Now in this example, we're going to use 3 by 3 matrix. So it's going to be kind of large. But let's take a look at how we will start with the system of equations and use what we know in order to solve matrix. Okay, so here we have a system of equations, 3 equations and 3 unknowns. And that's going to help us determine, we're going to use this information to come up with our F matrix, our X matrix, and then our G matrix. The G matrix is easy. It's always, in this case, the right-hand side, the n by 1 vector. So this is our G, as you can see here, whatever this G is. And our X matrix is determined by the components of x1, x2, and x3. So we have something that looks like this. So this represents the F and the G, and this is the X matrix that allows us to get our solution. In this case, they wrote it as a 1 by 3, but this really can be represented as a 3 by 1. And where am I getting these values for F? Well, I'm getting these values for F from the actual coefficients of the corresponding X values. So here we have here, and vice versa. So each row in F represents the coefficients for one equation. The second row represents the coefficients for the second equation, and vice versa. And the idea is if I were to multiply this by the matrix x1, x2, x3, then I will get this expression. All right. So the solution is this. Well, how can I determine the solution? Well, if you have your Inspire, all you have to do is find the inverse of this matrix and then multiply it times, we call this the right-hand side matrix, and then you will get this answer. And you can go ahead and check it. Push pause while you check to see if that works. Plug this into the Inspire and see, will F inverse times this matrix give me this? And that actually is our solution. Okay? Again, in order to do this problem, you have to determine that, first of all, F has to have an inverse. So this problem is easy if you have a graphing calculator, because a graphing calculator did the work of figuring out what the inverse of this F matrix is. But what if you don't have a graphing calculator, or what if you don't have the time to determine the inverse of a 3 by 3 matrix? Is there another process that we could use to solve this system of equations? And there is, and it's called Cramer's rule. Instead of involving inverses, it involves determinants. So let's take a look at a simple case for a 2 by 2 system. Again, we take our linear system, which will have two equations and two unknowns, and we represent this linear system as three matrices: our F matrix, our X matrix, and our G matrix. In this case, to make things simple, we're going to call our F matrix our coefficient matrix. Coefficient matrix, so A, B, C, D is a coefficient matrix. Our X matrix is X and Y, and our right-hand side matrix is E and F. Okay, so to figure out the values for this, our solutions X and Y, it's a matter of finding the determinant of our coefficient matrix, labeled it A, divided by and that's being divided by a determinant of a special matrix, and we call this matrix. It's not the coefficient matrix because it only has one row, one column of coefficients, and the other column is replaced with the right-hand side. I know it doesn't make sense, and if we had time, I would show you why it always works, but we don't have time. So in this case, if you notice, our coefficient matrix was A, B, C, and D, but then, so that's our A, but then this matrix looks very similar because it does have B and D, like right here and here, but the thing that is switched is it doesn't have the same column, and this column is the first column is replaced with the right-hand side matrix, and that's because we're trying to find the first variable X. To find the second variable, we replace in the coefficient matrix the second column. Okay, and that makes sense because if we're trying to find X, we replace the X column in the coefficient matrix, and if we're trying to find Y, we replace the Y column. And then we find the determinant of this matrix. So we're going to take a look at an example so we have an idea. So here's an example. And as you can see here, if I were to determine my coefficient matrix would be 5, 2, 3, negative 5. And to determine our replaced coefficient matrix, we replace the X column with 16 and negative 9. Okay? And then we evaluate the determinants and we get our answer for X. And we're going to do the exact same thing for Y. Here's another example, but this time with a 3 by 3 matrix. Well, not example, but another system. Here our coefficient matrix has 3 rows and 3 columns, and it's made up of A, B, and C. And we replace, in this case, we're trying to find X, so we replace the X column with, instead of A1, A2, A3, we replace it with the right-hand side. In this case, we're trying to find Y, which is the second variable, so we replace our B column in the matrix with our right-hand side. In this case, we're replacing the trying to find Z, so we replace Z with this. Okay, and we find the determinants of these two matrices. Actually, we're going to be finding the determinant of 4 matrices. The bottom value is always the determinant of the original coefficient matrix. Okay, so we're going to take a look at an example. Well, you can figure out how it works. Here's our linear system of equations. Here's our coefficient matrix, our A or our F, depending on how you want to look at it. And our right-hand side is 10, 14, 10. Okay. So then when we replace our coefficient matrix, we're going to replace the X column with 10, 14, 10, and we get that. We find the determinant of that. And we get our solution for X to be the result of that determinant of that matrix divided the determinant of our coefficient matrix. We do the same thing for the Y column. We replace our Y value in our determinant matrix with our X, Y, and Z. We find the determinant of that matrix is 56. Find the determinant, of course, the coefficient matrix is 28, and we get our solution for Y. And then we do the same thing for Z. And so that's all that it involves. Again, we have to have a matrix that has an inverse. And if you don't want to find the inverse, Cramer's rule allows you to find the solutions X, Y, and Z just by doing determinants. All right, that's it.